Alright guys, I said I'd do a couple of videos for you. I'm going to cheat. I've got them sort of all worked out for you so that the videos don't go on for too long. But let's see. Actually, I'm not going to cheat on one of them. Let's start with this particular one and talk about where you might have gone wrong with them. And this video is pretty straightforward. You actually have to consider the two conditions of equilibrium. So remember, condition number one is the sum of the forces equals mass times acceleration, and that has to equal zero because this is in static equilibrium. And we have a lot of forces acting on our beam. So we have a sign hanging down, I'll call that mg. And we actually have the mass of the beam pulling down. So that's capital Mg. We have the tension of the wire pulling over here. And we have some forces of the wall. The wall is pushing back with a normal force. And also, this is not slipping down. So we're going to assume that there's some friction there, and there's friction opposing the motion, because if there wasn't friction, the end of the beam would slide down. Okay, so if those are all of the forces, we can draw a pretty quick free body diagram. We've got the tension, we have the force of friction, and remember that's static friction. We've got the normal force of the wall, the mass of the sign, and the mass of the beam pulling down. Okay. All right, so that's condition number one. Condition number two is that the sum of the torques have to equal zero. So these two guys right here, if you're to cut this cable, they're going to both rotate in the clockwise direction, so that makes them negative torques. On the other hand, if you're to cut these signs up, this is going to rotate this way because of the tension, and that's going to be counterclockwise torque, and so that's going to be in the positive direction. Okay, so I think we're pretty well set up. Let's start with torque, because torque is the easy part. The sum of the torques is going to equal zero, so let's do our two torques. We've got mg, that's the mass of the beam, and that's applied at half the length of the beam, plus the mass of the sign, and that's applied at the full length of the beam, and that's equal to our tension times sine 40 and y sine 40. Well, it has to be perpendicular to the beam, and that's applied at the end, L. All right, so lucky for us, length cancels out because everyone's got length, and we can solve now for our tension. All right, so let's just do this quickly. What do we have? We've got 200 newtons divided by 2, that's 100 newtons, plus 50 newtons divided by sine 40 equals tension, and the tension equals 233 newtons. All right, so yeah, Jocelyn, I agree with you. AP made a mistake. I don't know what they did. It looks to me like they divided by sine twice, and then they used 9.8 meters per second squared as gravity, and the two of them combined to give their value of, I think, 352, but they're wrong. So sorry. Okay, so let's go back up here. Now that we know the tension, that was number A. They wanted to know the tension. B, they'd like you to find the components of forces from the wall. And that's actually pretty straightforward. We're back just to, Newton's second law here, Newton's second law. So let's think about it. The sum of the forces in the x direction. All right, so I've got to make a coordinate system. I'm going to call this positive y, and I'm going to call this positive x, mostly because that's the way the tension is pulling. And so in the x direction, I've got 0. And the two things I have acting in the x direction are the tension in the x direction. So that's tension cosine 40. And I can subtract the normal force of the wall, and that'll be 0. So that one's pretty easy to get. I get tension equals, let's see, tension cosine 40. So, where's my calculator? Tension cosine, so that's 233 times cosine 40. All right, so I get the normal force of the wall is equal to 178.4, we'll round it up, 9 newtons, right? So normal force of the wall. Okay, and I'm not in a hurry, so I can be picky. 3, 3. We could go 488, but 489 is fine. All right, so that's my normal force of the wall, and that's the force in the x direction. In the y direction, I've got to sum the forces up in the y direction. Again, they're in static equilibrium. And so how many forces do we have in the y direction? Well, we said that this would be the positive. So mg of the beam plus mg of the sine, and then I can subtract the tension in the y direction and the force of friction. Static, and that's going to give me 0. So these guys, let's see, what do we have? We've got 200 plus 50, and then I can subtract the tension in the y direction, and the way we define that coordinate system, that is going to be a subtraction, so we're good there. 233, whoops, clear. 233 sine 40. So that's minus 149, and that's going to equal force of friction. I'll just pull it to the other side, static. So 250. Okay, clear. Nice typing. 250 minus 149. We get 101 newtons for the force of friction. So significantly different than what AP gave us, but of course we don't agree with them with the tension. All right, I hope that helps. I'd say the third question that they might ask you is if you wanted to find the component force of the wall, right, then you'd actually have to take these two values. This would be the value up here in the x direction. This would be the value in the y direction. And you could do a squared in the x direction plus y squared in the b direction, take the square root in it, and you could get the component force of the wall. But they didn't ask you to do that. All right, hope that helps.